This is a BME 271 lecture on digital filtering 2. The topics of this lecture will be moving average window low-pass filter cutoff frequencies, high-pass digital filters, how to implement them in a couple different ways, and median filters. So in the last lecture, we introduced moving average low-pass filters, and these filters have a rect shape. And they are primarily characterized by their window width, the width of the filters. Okay? So let's say that we have a given input signal here, which is this string of numbers, right? Any given digitized signal is essentially just a list of numbers. Each one of these letters here represents some number. So if we have this input signal, the output signal, if we have a moving average window with a window width of 3, is going to be the average of every consecutive 3 numbers in this signal, in this vector. So for example, if the input vector is this, then the output vector, the first sample of the output vector, will be a plus b plus c over 3. Then the second one will be b plus c plus d over 3. And then the third one will be c plus d plus e over 3, and so on. You can see how this extends on up to the end of the vector. Now, applying this filter to a signal is equivalent to performing a discrete convolution of the signal with a rect function. So this is a function that looks like this as a function of time. We can plot here as a function of time the samples of a window width 3 moving average filter. And of course that goes on and is all zeros till the end of time and zeros at the beginning of time. The magnitude there is 1/3. And the index here is n, so this would be n equals 0, plus 1, minus 1, plus 2, minus 2, and so on along the n-axis. Now, as you know, the wider a time domain signal is, the narrower its Fourier transform is. And we've already seen that a rect, or a constant window function in the time domain, in the continuous time domain, is a sinc function in the frequency domain. We talked about that last time when we were talking about the drawbacks of moving average windows. Now in the discrete time domain, in the discretized time domain, a rect function transforms to a function that looks almost exactly like a sinc function, but is actually called a Dirichlet kernel. And we're not really going to see this in any other context here. I just want to be precise about what we're talking about. Because we're going to use this mathematical form essentially to figure out, it's based on this mathematical form figuring out what the cutoff frequency is of a moving average window. So this is the mathematical form of a Dirichlet kernel. It turns out that it's almost exactly the same thing as a sinc. You can see that it has this sine x over x kind of form. And here the k is a frequency index, so that's the index into the frequency axis. N is the number of time points in a given signal that we have discretized, on which we have discretized the rect function, and little n is a time index, okay, which we haven't used here actually in this example, but in WW is the window width. Now this sinc-like Dirichlet kernel has magnitude 1 over root 2, or minus 3 dB on the dB scale, at frequency f sub c, or the corner frequency, of 1/2 times f sub s over WW. So again, WW is the window width of the filter. And f sub s is the sampling frequency that was used to sample the signal. You guys have had some experience now setting sampling frequencies in LabVIEW. And so that if you had a given sampling frequency and you applied a given window width, if you had sampled a given signal with some frequency like 1 kilohertz or so, and you had a window width that you were using to do a moving average filter on your signal, then the cutoff frequency of that moving average filter would be given by the sampling frequency you used in LabVIEW divided by the window width you used in wherever you applied the filter. Okay. Now another way to write this is that this 1/2 f sub s over WW is equal to 1/2 times 1 over WW times delta t, where delta t is the step in time between consecutive samples in our sampled signal. So it's equal to 1 over fs. And WW times the step size between samples gives us actually the duration of the moving average window in time. So this is perhaps a little bit more intuitive way to think about the cutoff frequency. Okay, so the cutoff frequency is 1/2 times 1 over the duration of the moving average window in time. Pretty simple expression. And so then the units of this would be in hertz, as you can see. So that was low-pass filters. That discussion of cutoff frequencies finishes off our discussion of low-pass digital filters. Now let's move on to high-pass digital filters. So a high-pass filter is a filter that will only keep rapid changes corresponding to high frequencies in our signals. Okay? And we saw earlier that when we applied a high-pass filter to a square wave that we only got the changes in the signal. So intuitively what we might expect to get from a train of numbers from a very simple high-pass filter might be something like the differences, the consecutive differences between samples, since that would be like an approximation of the derivative, right? So then this first output sample would be B minus A. The second one would be C minus B. The third one would be D minus C, and so on. So we're emphasizing, we're only passing here the differences between consecutive samples. So now it turns out that the direct design of high-pass filters can be tricky. Fortunately, though, we can simply note that a high-pass version of a signal has to be equal to the signal itself minus some low-pass filtered version of it. And we've already seen how easy it is to apply low-pass filters to signals. And so this follows from just linearity of Fourier transforms, in that if we apply a low-pass filter to a signal, we have essentially suppressed the high-pass elements while only leaving we've suppressed the high frequencies and only left the low frequencies. So if we subtract that from the signal itself, then that must leave only the high frequencies. And again, since we already know how to do digital low-pass filtering, we can implement digital high-pass filters this way pretty easily. So that's one way to do it. So let's illustrate this with an example. Let's say that we have the following Vn signal. It starts at 0 for 4 samples, then it goes to 1 for 4 samples, and then it goes back down to 0 for 4 samples. Okay, and this is the index into the signal n, the integer index n. And so up here is 1, and this is 0. Okay, now let's say that we then low-pass filter this guy, since the first step in our high-pass filtering is to actually low-pass filter the signal. Let's say that we low-pass filter it with a window width of 3. What we're going to get then is, let's see, we'll get the first 2 samples will be 0. The next sample will be 1/3. Then we'll get 2/3. Then we'll get 2 1s. And then we'll get 2/3 again. 1/3, and then 0 for 2 more samples. So it's going to have this sort of humped shape now, smoothed out humped shape, where this guy is 1/3, this is 2/3, and this is 1. Okay, so this is what we get after low-pass filtering with a window width of 3. So now if we subtract the original signal from subtract the low-pass filtered signal from the original signal, what we will get is the high-pass version of the signal. So if we now take Vn minus LPF of Vn, then what we will get is the following. The first two samples will again be 0. Then we'll get a minus 1/3. Then we'll get a plus 1/3. Then for the middle two samples in the plateau, it'll be 0. And then it will go plus 1/3 and minus 1/3 again. Okay, and so what we have here is that by subtracting the low-pass filtered version of our input signal from the signal itself, we have left only the edges that we suppressed using the low-pass filter, right? So we subtract off sort of the local average value, and we're left with only the edges, which is what we would get from a high-pass filter. Another way to implement a high-pass filter that is perhaps more commonly used is to take a low-pass filter that we have. Let's say that we have a sampled low-pass filter h of n. So recall that h of n here, for example, for a moving average filter would be just a vector of 1s. And what we can do with it then is shift its transfer function as a function of frequency. We can shift it to be centered at some other frequency away from DC by multiplying it by a complex exponential of this form, where m here is the frequency that we want to shift it to. And so what that will give us after taking the Fourier transform of that is the same transfer function that the filter had originally, but it will be shifted by m samples as a function of frequency. Okay, so just to say that more explicitly here, this is a phase modulation that we apply to the samples of our filter. And this is the transfer function that is shifted by m as a function of frequency. So the idea here is that if we have some low-pass filter here, and this is DC, then what we can do is we can apply this phase modulation and shift it to be centered at frequency m by multiplying by this phase modulation. So this second signal here is the high-pass filter that we obtained by this phase modulation, and the first signal is the original low-pass filter that we had before phase modulation. And again, little n here is the index in time, and capital N is the total number of samples in our signal. So let's do an example of this. Let's say that we have capital N is 1024 samples collected at a sampling rate of 1 kilohertz. Now, given some low-pass filter h of n, such as a moving average window, which would then comprise just a set of 1s, what should little m be here to shift the filter to be a high-pass filter that is centered at 500 hertz? Note that 500 hertz is half the sampling frequency of 1 kilohertz. Okay, so to do this, what we have to do is we have to convert the desired shift of 500 hertz into an index, into a frequency index, into the discrete Fourier transform of our signal. Okay, so what we're going to do here again is to convert the hertz into a frequency index. And the way we're going to do that is to use the following relationship, which is a new relationship, which is that the 500 hertz that we want to shift by divided by the sampling frequency of 1 kilohertz has to be equal to little m over capital N. Okay, 500 hertz over 1 kilohertz has to be little m over capital N, which is 1024. And this relationship holds because the sampling frequency f sub s says what the width of our frequency of the width of our signal as a function of frequency after we have sampled it using that sampling rate. And that also corresponds to capital N frequency samples. So if you sample a signal at rate f sub s with a total number of samples n, and you calculate its discrete Fourier transform, then you're going to get a Fourier transform of width, total width f sub s. It'll go from minus f sub s over 2 to plus f sub s over 2. And there will be a total of capital N samples in that discrete Fourier transform. So it has to be that the shift is proportional that we're applying here, and so this relationship will then hold, and we can use this to solve for the frequency index to put into that phase modulation function that we showed on the previous page. So if we do this, then we solve. If we plug in 1,000 for f sub s and 1024 for n, then of course we get 1/2 equals m over 1024, and m must be equal to 512. So now that we've solved for the fact that little m has to be 512, let's look at what h of n would then look like if it were a moving average filter with window width 5. So then the question is, what does the final high-pass filter look like? Well, starting out, we have the h sub n, which looks like this. It's going to be mostly zeros, but then it's going to have 5 non-zero samples of height 1/5. And then it will continue on and be 0 on either side as a function of n, and this is 1/5. And if we plug in the value that we solved for little n, and the value that we're given for capital N, so little m is 512, capital N is 1024, then we get 1/2 there, that cancels with the 2, and we get that the modulation function is actually just e to the j pi n, which simplifies to -1 to the n. So we're either multiplying the signal by 1 or -1, depending on whether we're at an odd or even index. Okay, so when we do this, then we will get the following. When we apply the phase modulation, we'll get the following. We'll get still 0 samples at the beginning, and then every other sample is going to be negated in our moving average window. So that's 1/5 and -1/5. Okay? So this right here is the high-pass filter that we derived by using this method. So if we apply this h of n to a given input signal, we will get a high-pass filter version of that signal. Okay, and that concludes our discussion of high-pass filters. The last kind of filter that I want to talk about is a really cool one called a median filters, or perhaps better called moving median filters. And to introduce them, I want to introduce them in contrast to low-pass filters and high-pass filters. Low-pass filters and high-pass filters are linear, or at least the kinds we've been talking about are linear, meaning that if we have some given filter h of x, which is a filter applied to some signal x, right? So if y equals h of x would be some filtered version of the signal x. Then if we take some linear combination of two signals x and y by multiplying them by some scalars a and b, then what we're going to get at the output of the filter is going to be a times h of x plus b times h of y. Right? This is the definition of linearity for a given filter. Now usually linearity is a desirable characteristic, and the filters we have talked about so far all possess this characteristic. Median filters, however, are different. They are nonlinear, but they're still quite useful in practice. And they're implemented by calculating a moving median rather than a moving average, as in the case of the moving average windows that we talked about previously. So essentially what we do is we just move a window along and calculate the median of the samples rather than their mean. And that implements a median filter. Okay, so as we often do, let's demonstrate this by example. Let's say that we have a signal that has a giant spike in it. It's an artifactual spike that maybe was caused by, again, one of the sources we talked about of spikes was brushes and motors wearing out. Okay, so let's say we've got this signal. I'll plot it roughly here. It's going to, have some pretty normal values, but then it's all of a sudden at this one value going to have a giant spike where it spikes up to 1,000, and then it continues along its merry way there. So that's the original input signal. This is in, and it contains this giant spike that is an artifact that we would like to remove. Okay, if we low-pass filter this guy, then you can see that we more or less have the signal that we care about for values away from the spike, but in the spike itself actually gets blurred out a lot. Okay, so if we were to draw that, it would look something like this. It sort of reasonably well track the original signal, except for here it would like blur out the spike, and you'd still have this giant effect on your signal due to the spike. And note that I can't really draw a spike that is 1,000 times bigger, so this would really be blurred out to some value that's much larger than what I'm able to capture in this drawing here. Okay, so really it just makes the problem worse to do low-pass filtering on the spike, because you're still leaving over all the low frequencies of the spike. If you recall, the spike contains energy at all frequencies. And so if we low-pass filter it, we're only suppressing the high frequencies of the spike, but we leave all the low frequencies, so you get this blurred-out version of the spike. On the other hand, if we calculate the moving median of the signal, we again get almost the same signal everywhere else, just as in the low-pass filter case. But the cool thing is that the spike is completely ignored, right? So in this case, what we would get with the moving median filter is essentially the same thing, but it would track the original signal much more accurately right by the spike and completely ignore the spike itself. So it has effectively removed all the frequencies of the spike, which is kind of an amazing result. And here the median filter length was 3. You can see that in comparison to the low-pass filter, the median filter did not blur out the spike at all. It just completely removed it. So again, what happened here is that the spike had energy at all frequencies. The low-pass filter suppressed its high frequencies but left its low frequencies, which just blurred it out in time and really made it worse. The median filter completely ignored the spike, or effectively suppressed the spike completely at all frequencies. And the reason it can do this is because it's a form of a nonlinear filter. Unfortunately, that means we cannot use Fourier analysis to help set the window width. Right? There's no cutoff frequency that we can define for a median filter. Still, what happens in practice is that wider windows tend to smooth more, wider median windows tend to smooth more, and will be more robust to spikes that occupy multiple consecutive samples. So still, the idea that if you use a wider window width, you'll smooth more, holds for median filters also. Median filters, though, have this interesting property that they are edge preserving, which makes them very interesting for a lot of applications. So they won't blur out edges in your signal. So here's a really cool example of a 2D median filter applied to a discretized image that I got from Wikipedia. So essentially what they did here was they took some original image and they knocked out random samples from it. And you can see that it's extremely hard to see what's going on there. You can't really make out any details of the woman's face here. So it's really a completely useless image. But by putting a moving median window, a 2D moving median window, it's probably maybe a 3x3 or 5x5 window that they used here. So they basically just took a 3x3 or 5x5 section of the image centered at each point, move the window to be centered at different points in the image, calculated the median over that 2D domain, and then set the value of the output image, the filtered image, to be that median of that local domain. Then they get this image on the right, which is substantially improved, right? You can definitely tell out the features of her face, etc. So it's a pretty impressive filter that has found a lot of interesting applications. So that wraps up our discussion of digital filters. To summarize from today, what we talked about was the cutoff frequency of low-pass filters, how to set that based on the sampling rate that you have of your signal. We talked about high-pass digital filters that can be implemented either via subtraction of a low-pass filtered signal from itself or via phase modulation of some low-pass filter, right? We talked about that using the Fourier shift theorem. And we finished up talking about median filters, which are good for removing spikes in our signals. That's where where you guys are going to see it most. You could actually implement it pretty easily in MATLAB to remove any spikes that you might get in the signals that you're going to be measuring using, in particular, as your projects move along. There may be certain projects where your transducer is sensitive to spikes that might get into the signal, and you can use median filters there to suppress them.